Hello, am I audible?
Good evening, sir.
Yeah, good evening. Santosh, I'll start in few minutes. Let others also join. Okay.
Yes, sir.
Yeah. So you can keep your camera switch off meanwhile if you want. No issues.
Okay.
Yeah.
Definitely.
Okay. Okay, I guess so far no one has joined. We can start. Am I audible? Hello? Santosh, are you there? Am I audible? I think you are muted. I cannot hear you. Hello?
Yes, sir. बोलिए, sir.
Okay. So let us start the session. So before starting, let me just. So I think you didn't join in the last lecture, last tutorial, week 1. Am I right?
Sir, this is my first class, sir.
First class. Okay.
Yes, sir.
So what do you actually do? Like, you can just give a brief introduction about yourself. Like you are pursuing your PhD or something, your master's. Hello.
Sir, tell me, sir.
I'm saying that are you pursuing your PhD or you are just working only
No, no, no.
somewhere,
I'm continuing PhD. Yes.
continuing PhD?
Yes,
PhD from
yes.
where?
NIT Rourkela.
NIT. Okay. All right. And uh, so I guess one other student has joined. Okay. So you are a full-time PhD, right?
No, sir. No, sir. Executive
Okay, you
PhD.
are. Acha, part-time. Okay. So what motivated you to join this course?
Sir?
I'm saying that what motivated you to join this course? Like why you
Yes, I have joined in the course. Yes, sir.
like what motivated you? Why you joined it?
For research, regarding sir fundamental understanding and research about the CFD
Research.
analysis, I have taken one
Oh,
project regarding CFD.
okay. Okay. All right. All right. So let me turn on my camera. Let's start. So my name is Varnit Kapoor. Am I visible? I think visible. So my name is Varnit Kapoor, and I'm also pursuing my PhD from IIT Delhi, and I will be taking up this tutorial session. So I hope that you have watched this week's videos, lecture videos taken by the professor. Santosh, am I audible? Hello.
Yes, sir. Audible, audible. Sir.
Yeah, I'm asking that have you gone through the tutorial videos? The last
One
tutorial video one?
only one video I have seen. One lecture only I have seen. Sir.
Like you have seen the lecture video or the tutorial video? The one which I took or the one lecture videos taken by the professor?
Only one lecture video I have seen already. Not tutorial
One
video.
lecture.
One lecture video I have seen. Yes. Sir.
Okay, okay. All right. So I would just request you that you just watch the lecture videos also because there are assignments which you have to cover up. And the tutorial video also you can see
Sir,
if you
your
want.
sound is very less, sir.
Uh,
If it will be increased, it may be increased. Very less, sir.
is it clear now? Hello?
Yes, now clear, sir. Okay, sir.
Now clear? Okay, okay, okay.
Yes, sir. Clear, sir. Okay.
Yeah, okay. So I'm saying that uh, it would be good if you watch the tutorial videos, the one I have taken in the last class, as well as if you watch the lecture videos basically first before coming to the lecture. That will help you a lot. Okay, no problem because we have to do the assignments also. So that's very important. All right. Uh, Bhupata. Okay. Bhupata, I'm audible to you also as well. Are you there?
Yes, sir. Yes.
Yeah, yeah. Okay. So I see that you joined this tutorial session first time, right? I think you were not there in the last session. Bhupata, what do you do? Like you are a student or a working professional?
Yes, sir. I am student. I am fourth year student of mechanical engineering.
From which college?
I am from Faculty of Engineering, Maharaja Sayaji Rao Gaikwad, Vadodara.
Okay. Okay. All right. So what motivated you to join this course?
Sir, the basic thing is that I started much like that. I have done a course on fluid mechanics by
Okay.
NPTEL.
Okay.
So the next step, I think, this is like this and like open form and all these things to learn.
Okay. So you want a basic understanding of discretizations of the equations
Yes,
and
sir.
how the mathematical it works. Okay. Okay. So you have
I
watched
know the
the.
basic conservation and all things, but
Hmm.
I know the basic conservation and all these things, but I am not really very aware about the all the finite elements and finite volume and all these things.
Okay. So you have watched the lecture videos taken by the professor.
Yes, sir.
The
I watched I think 2 weeks, 2 weeks lectures.
2 weeks lectures. Yeah. So you have done the assignment.
Yes, sir. I've
Any of
done.
that? Okay. Great. Great. Okay. So no problem. So today I'll be taking the week 2 tutorial. Whatever has been done in the week 2 by the prof. And based on that, that assignment has been given to you guys to solve it. So I'll just take up what has been done. We'll do a few questions, some statement problems, and yeah, in this. And if you have any doubts, we will discuss all those things as well. No issues. Okay. So let us start. So let me just share my screen. And you can stop me at any point if you have any doubts. I hope my screen is visible now. Hello? Is my
Visible,
screen
sir. Visible.
Yes, sir.
visible? Okay. All right. So maybe others will join later. Let us start doing the week 2 tutorial session. All right. So far, Professor has in week 1 tutorial, I discussed about the energy equations, mass conservation equation, and the momentum equation, Navier-Stokes equation. Okay. So all this, and I have uploaded that on my YouTube channel as well. And maybe you might have got the links or the sheet on your email as well as you can see on the course page. All these things. If anyone has any doubts, I've discussed. Few students joined in the last tutorial. And I also want you guys that you be consistent with the tutorial sessions. So that will help you. Any doubts you have, we will discuss everything. We'll do some questions. So for that, it will be very helpful to all of you. So yeah. Okay. So basically, we did some few equation, and the derivation has been done by the prof for each and every part. So I'll give a brief what has been done. Okay. So like recap of the all the 3 4 lectures what has been done, and we will start with the questions. Okay. So the conservative form of the governing equations of the fluid flow from the past week 1 lectures. I'll just write down the equations once again. Okay. So governing equations of the flow, or you can say conservative form of the governing equations. I hope whatever I'm writing is visible to you all.
Yes, sir. Yes.
Okay. Of fluid flow. Okay. So first equation was the mass conservation. Mass conservation. So the equation was dou rho by dou t plus divergence of rho u is equal to 0. This is the mass conservation equation. So these are the governing equation of the flow of a general compressible Newtonian fluid. So as per like it's a incompressible and all that you can do to satisfy the conditions. Next is the x momentum. X momentum. So the equation was dou rho by dou t And all the derivations has been done in week 1 lectures by the prof in their lectures. And you can refer their videos or sessions. Rho UU is equal to pressure gradient with respect to x plus divergence of mu grad u. Mu grad u plus some source terms. Similarly, y momentum equation. So this equation is dou by dou t of rho v. U v w are the components of the velocities. Rho u v u. Okay, this u is just thing but a vector u. Okay, so I'm just making it a bit bold, which comprises of all the velocity components, dou p by dou y plus divergence of mu grad of v plus source terms in y direction. Similarly, z momentum equation is dou by dou t of rho w plus divergence of rho wu is equal to pressure gradient in z plus divergence of mu grad w plus source term in the direction. And the next equation is internal energy equation, which we had. Internal energy equation was dou by dou t of rho I or rho E, whatever you can take. So it is a specific internal energy per unit mass. Divergence of rho I or U instead of E, I am taking I. Okay. Then the pressure, negative of pressure, divergence of U plus divergence of the coefficient K grad of temperature plus phi term plus again source. So phi term has some enormous amount of terms in it. So that has, I will not write it down. I'll just give a brief that this was the equation. You can see in the proof videos. Okay. And next one were equation of states. Equation of state. An equation of state. One was pressure is equal to dependent over density and time, and internal energy, specific internal energy, is dependent over density and temperature. Sorry, not time, temperature. Like example, if I say for a perfect gas, we know one gas law is P is equal to rho RT, and we know that internal energy is equal to CVT, specific internal CVT. Okay. So these were the brief equations which has been used. Now we will come to the differential and integral form of general transport equations. Okay. These were the momentum equations, energy equation, or mass conservation equation. But we will come to the general transport equation if we have. So there are significant commonalities between the various equations. So if we introduce a general variable phi, okay, no, we don't take a variable UVW or some internal energy. If we say there is a general variable y in the conservative form for a fluid flow equations, which includes the equations for scalar quantities such as temperature, or you can say some pollution concentrations are there. So how you will write that equation? So I'll not go into the proofs of the equation. Already that has been done in week 2 lectures by the professor. So I'll just write down, give a brief of what has been done. Okay. So let me write down the heading first. differential. And you all can ask me doubts if you have, so that it's a recap for you guys as well. And it can be a doubt clearing session as well. Integral forms. And towards the last, when we'll come to the finite difference method, I'll introduce one more method there, maybe which has not been covered in the lecture videos. I think so. I'm not sure, but I'll definitely discuss that one thing of the general transport equation. So how you will write the equation, that will be dou phi by dou t. Now instead of UVW, you will write as phi is the variable, plus divergence of rho, the variable phi, u, where u is the complete vector of comprising of UVW, complete velocity. And then divergence of, instead of viscosity or thermal conductive coefficient, we'll just use a tilde, which is a very grad phi, general coefficient tilde, and grad phi plus some source type. Okay. So in other words, you can say that rate of increase of this phi is a general. Let me write it here. Phi is nothing but a general variable. So general variable. Okay. And in other words, we can say rate of increase of phi of a fluid element, which is the first term. The physical significance says that this is the rate of increase of phi of that fluid element plus this is net rate of flow of phi out of the fluid element, net rate of phi, net rate of flow of phi out of fluid element. That is nothing but a which term? We can say it is a convective term. It is convecting the fluid when the fluid is, someone has joined. So how much of the flow is convecting out of the fluid element? Net rate of flow of phi out of the fluid element then this term is rate of increase of phi due to diffusion. This is a diffusion term. Rate of increase of phi due to diffusion. And the last term, rate of increase of phi due to some source terms are present. Rate of increase phi due to source, due to sources. So this is a general transport equation. Now what you can do, you can apply basically a control volume analysis over that. So this equation is called the transport equation for a property phi, and it clearly highlights the various transport processes where the rate of change term, convective term are on the left hand side, these two terms, and The source term and the diffusive terms are on the right hand side. These two terms. Okay. So in order to bring out some common features, yeah. Any yes?
Sir, so this is basically looks like a Renault transport theorem.
No, Renault transport theorem is something else. So when I will do some integration and take out some terms, RTT is something else. This is not RTT. This is a general integral form of an equation. A general equation so far, differential form of an equation. Now we will do the integration.
Sir, but Renault transport theorem also says that if we want to find the changes of property, any property inside the control volume.
So have I discussed anything about control volume so far? This is
Sir,
not
this
integrated over
analysis.
a. No. I have not done anything over integration of a control volume over a control volume. Have I done? So RTT does
Okay.
something that how the transport of the fluid is happening from over a control volume from one position to another, and that there is a common that how much it is being stored, how much has been taken in, and how much has been taken.
Okay,
Right.
sir. Okay.
So this is not a RTT. Okay. Yeah. Yes. So where I was. So we had to hide. So obviously we had to hide some terms that are not shared between the equation in the source terms. Of suppose if you don't want, and make it work for only for internal energy, we can work for only conservation energy. If you put phi as 1, phi as u, or phi as I, so all these three equations you will get: momentum equation, mass conservation, internal energy equations. If you put phi as 1, u, v, w, I, you will get this the same equation from all these three equations out of that. And selecting the appropriate values for the diffusion coefficient and source terms can be done accordingly. Okay. So you can say that there are 5 partial differential equations, 3 for momentum, 1 for mass, and 1 for energy conservation. So the key step of the finite volume method we will come when in the coming lectures. But basically what there is done is that there is an integration over a 3-dimensional control volume. Okay, now we will do some integration. And that volume integral, if we do a control volume integration over this general transport equation, then the volume integral in the second term, the volume integral over the second term on the left hand side, this red highlighted, okay, and the convective term, okay, in the first term on the right hand side, this diffusive term and the convective terms. So if I do a control volume and apply a Gauss divergence theorem, we can do some Gauss divergence theorem on that, and we will get a final equation out of it. So let me do the control volume of integral over it. First, let me write integration over a 3-dimensional of above equation over a 3-dimensional control volume C, which will yield you with volume of dou rho phi over dou t dv, because you are doing an integration. Okay, so dv is the complete volume of that element, small element. Divergence of rho phi u dv is equal to control volume integration over divergence of the diffusion term grad of phi dv plus integration over source term. Okay. And you can do apply Gauss divergence theorem over this term over this term. Okay. So then you will do a Gauss divergence theorem, GDT, what you will get. So what is a Gauss divergence theorem? Can anyone tell me? What does the Gauss divergence theorem do?
Not known, sir.
Santosh?
Not known, sir, actually.
No, you don't know. Okay. Bhupata? Bhupat. What is your name actually?
Bhupat, Bhupat.
Bhupat. Okay, Bhupat. What does this do?
Sir, it is like that divergence of any term, like that
Mhm.
divergence of any field over
Okay.
control volume
Yeah.
is, I think I don't know the second term. That is the main thing.
Okay. So basically, it integrals over the entire bounding surface of the control volume. Okay. So suppose if you have, let me tell what GDT is. So if you have a divergence of any field, suppose field is A, capital A, and you are doing a integration, control volume integration over that field. You have a divergence of a field A. You are doing a control volume integration over that field A. That will convert into a surface integral, that is surface S, and the normal to that surface dot n dot the field A and dA, the surface area. Sorry, ds I should write ds. So del dot AdV is equal to n dot A ds. Okay, this is a, and physical interpretation of this n dot A is nothing but it's basically the component of a vector in the direction of that vector normal to surface element. Okay, to surface element. So the integral of the divergence of a vector over a volume, integral of a divergence of a vector A over a volume is equal to component of A in the direction normal to the surface, which bounds the volume over the entire bounding surface. This is the Gauss divergence. Is it clear? Any doubt in understanding this part?
No, sir.
What a Gauss divergence theorem is? Hello?
Yes, sir. Okay.
Oh, I think I've lost my network. Am I audible? Hello?
Yes,
Yes,
sir.
sir.
Hello? Okay. I think there was connectivity issue. Let me again share the screen. I hope my screen is visible. Hello?
Yes, sir.
Yes, sir.
But why I'm not able to see my screen? Ah, Yeah. So I was saying that about the Gauss divergence theorem. I hope you guys were able to understand.
Very less sound, sir. Not audible. Very less sound.
Very less sound. Am I audible now? Hello? Am I? Hello?
Yes, sir.
Is the sound clear now?
Yes, sir.
Okay.
Very low.
So Santosh, maybe you can increase your system volume. Maybe that might be a case. I'm not sure. Bhupat, is it with you as well? You are also.
No, sir, it is clear.
It is there. So I think Santosh, can you increase the volume of your system from the device which you
Okay.
have joined?
Okay.
Yeah, maybe. Okay. So I was saying that the physical interpretation of the Gauss divergence theorem is that it's basically nothing but you are this n dot a is the component of a vector in the direction of a vector normal. So the integral of a divergence of a vector a. Let me highlight once again. Integral of divergence of a vector a, a capital A, over a volume is equal to the component of A is equal to the component of A in the direction normal to the surface, which bounds the volume over the entire bounding surface area. That is capital S. Is it clear? The Gauss divergence theorem? Or you guys have any doubt?
Clear, sir.
Clear? Okay. So del dot AdV is equal to n dot AdS. Simple as that. So we will apply the Gauss divergence and write this equation dou by dou T of control volume rho phi dV plus control surface S or A you can write n dot. The property is rho phi U over dV or dA this time. dA is equal to over control surface n dot grad tilde grad phi dA plus control volume S phi dV. S phi dV. Okay. So basically it depicts the rate of increase of phi plus net rate of increase of phi due to convective across the boundaries is equal to rate of increase of phi due to diffusion across the boundaries and net rate of creation of phi. This equation generally depicts this. Then you are doing a control volume analysis. I'll write that thing also. So this term says the rate, I'll write rate of increase as ROI. Every time will not write of phi. Net rate of decrease, this term is net rate of decrease of phi due to convection across the boundaries. Then this term is rate of increase of phi, ROI of phi due to diffusion across the boundaries. The boundaries. That's his net rate of creation of phi due to source. Net rate of creation of. Okay. Is this much clear? Or any doubts in this?
Sir,
Yeah.
sir, how can we say that it is increase or decrease? It cannot be like it is only rate of change of or
So you tell me one thing. When a fluid is flowing from in a channel, okay. So from one
yes,
cell to another cell, that fluid will flow, correct?
yes, sir.
So from that one cell to the another cell, if your system is the first cell, there will be a decrease in that cell. And that has happened because of the convective process of the flow. So there will be a decrease in that cell. Okay. And similarly, when there is a flow where the diffusion is happening, so diffusion will always increase, always what it will do, spread out, the fluid will spread out in such a way and it will diffuse, which will automatically increase the rate of phi or any property UVW whenever there is a diffusion process. When you suppose you take a there is a water and you pour a ink drop of ink, it's a diffusion process, right? When you drop a ink, it diffuses automatically in the whole liquid. It's a physical phenomena seen in the nature. So that is why there is an increase of all the properties because of that diffusion process. Is it clear why there is a decrease and increase?
Okay, sir.
Okay. Yeah.
Thank you.
Okay. Someone is trying to join. Okay. Geetika, am I audible? I don't know. She's trying to join. Yeah, am I audible? Hello? I cannot hear you.
Yes, sir, you're audible now.
Okay, okay, all right. Okay, so and generally there are we deal with the problems where our steady state problems are there, suppose. So in the steady state problem, this term will be zero because there is no change with time. So this leads to only with this part of the equation is left with us. Okay, it's not time dependent. But if it's a time dependent, it is also if there are unsteady state problems, which we will do in the coming week tutorials and the lectures as well. So if there is a time dependent problem, so then it is necessary to integrate with time as well over a small interval dt or delta t, sorry. So say from time t to time t plus delta t, you need to integrate over that delta t as well. So I'll write that single statement. Uh, yeah. So for time dependent problems, I'll write for time dependent problems. Time dependent problems. It is necessary to integrate from time t to integrate over small interval delta t, that is from time t to time t plus delta t. So what I'll do, the equation will be looks like something like this: integration over delta t, dou by dou t, then integration over control volume of the first term, rho by dv, and integration over dt. Okay, because of this dt is there, and because of control volume dv is there. Okay, so plus again for the convective term. So this is over control surface because of Gauss divergence, rho by u dA as well as dt equal to integration of delta t area n dot grad of phi dA dt plus again delta T, control volume of the source term, dV, dt. dV. Okay, so this is a for a. All right. So all the proofs, everything has already been done in the lecture videos. I'm just giving a brief that what has been done so far. Okay. Now classification of the physical behavior of the fluid. So now we have derived the, or we have seen, not derived, basically seen the conservation equations of the fluid flow at the time is that over the time as well, integration over the time as well. So there are different kinds of fluid flow in a physical behavior. One is the equilibrium problems are there, or another is the marching problems are there. Okay. So let me write classification of physical behavior. The first one is equilibrium problems. And second one is marching problems. So equilibrium problems are basically are steady state situations. Okay, the steady state distribution of like a temperature in a hello. Oh, someone has joined. Mohanna P. Okay. Okay. Mohanna, am I audible to you? Hello. Okay. Anyways, so I was saying about that equilibrium problems are basically the steady state problems. Like if you see a distribution of a temperature in a rod of a solid material. So equilibrium stress distribution of a solid object under a given applied load is another case. And various other steady state fluid flows are available in the nature. So these are governed basically by elliptic equations. Okay. So prototype elliptic equation is like one you have seen in your basic fluid mechanics courses, a Laplacian equation which describes the irrotational flow. Okay, for grad square of phi equal to 0, basically, where phi is the potential function. Okay, or you can also say rotational flow of an incompressible fluid, or you can say steady state conductive heat transfer. So, like we can say, let me write first. So I request you all that you please watch the lecture videos uh, because that will give you, before coming to the tutorial session, that will give you more confidence and ability to solve the questions as well as to discuss any doubts with me. So make a most use of it for these tutorial sessions. So I was saying about the equilibrium problems are equilibrium problems are basically steady state situation, include steady state situations. Okay. One is like I told, grad square of phi equal to 0. This is a Laplace equation for irrotational flow of an incompressible fluid. Okay. And the equation seems to be like dou square phi by 2x square, writing this equation only, plus dou square phi by 2y square is equal to 0. And a very simple example of an equilibrium problem is steady state heat conduction, where there is an insulated rod of a metal whose ends are Suppose you have an insulated rod of a metal. Suppose you have this is a rod and it has been insulated by the outer environment, from the outer environment, and at T, this x is equal to 0 position, T is equal to T naught, and at x is equal to L position, T is equal to TL. Okay, and if it is insulated, so definitely heat flux Q will be 0. No heat flux will be. So it is kept at a constant temperature, but different temperature are maintained at different positions. So in one dimension, how you will represent this equation? You will represent like K dou T dou 2T by dou x square equal to 0. Nothing else done. This is a rod insulated of length L, of length L. So how you will make a graph, how you will show it over a plot is like somewhat like this. So x is equal to 0 and x is equal to L for the rod. The temperature is T naught at x is equal to 0 and L is TL. It's nothing but a linear variation. When you will integrate this twice, you will get some constant that you have done these boundary value problems. Okay, a unique solution is there for the elliptic equations and can be obtained by applying some specific conditions. You know, these boundary condition, these two boundary conditions for the same. Okay, and you can integrate. So important feature of these kind of elliptical equations is nothing but is that the disturbance in the interior of the solution, for example, the change in temperature due to sudden appearance of small heat sources there. Okay, or disturbance signals are traveling in all directions. So these kind of equilibrium problems are nothing but steady state problems. Okay. Next categorizations are the marching problems. So marching problems. So in marching problems, there is a transient heat transfer and all unsteady flows are there. Wave phenomena are the example. Okay, where the marching problems happen. And these kind of equations are generally parabolic or hyperbolic equations. There are, if you have a general PDE, so you will observe that a particular kind of equation behavior it will show. It's either it's a parabolic, elliptic, or a hyperbolic. We will see the case. But however, in the equilibrium problem, it's a it's a elliptic, and for a marching problem, it is parabolic and hyperbolic. Parabolic and hyperbolic. But however, not all the marching problems are unsteady. They can be unsteady, but it is not necessary they will be unsteady. Okay, so we will see that how for a parabolic and steady flows, parabolic and hyperbolic equations are formed. So in these cases, the direction acts like as a line-like coordinate for marching. So with time, how the solution is marching in that is why it's a transient problem. So parabolic equations are nothing but a time-dependent problems which involve, you can say significant amount of dissipation. Example, you can say unsteady viscous flow and an unsteady conduction, heat conduction is there. So how you will write that parabolic equation in diffusion equation? So you know the general equation. You know this is a general equation. This equation. This is your general equation. So I'm saying just it's an unsteady diffusion equation. That means this is unsteady term. This is unsteady term. This is a diffusive term. Also convective term. This is a diffusive term, and this is a source term. When I'm saying it is an unsteady diffusion equation, that means only this term will be there. Only this term will be there, and this term will be there because this is unsteady. This is diffusion. When I'm saying unsteady convective problem, that means this term will be there and this term will be there. The rest everything will be zero on right hand side. Just the convective problem. So just from looking this equation, you can derive any equation. You can come up to any equation. You see that. So let me write here. So parabolic equation, suppose these are, first let me write transient, unsteady. So these are steady state situations. These are transient, unsteady situations. You can see. Okay. Another thing is that governed by parabolic or hyperbolic equation. I have written elliptic there. I have not written elliptic equations. These are parabolic or hyperbolic equations. So one of example I can take unsteady heat conduction or diffusion equation, parabolic diffusion equation. It is nothing but dou of dou T unsteady of any property phi is equal to any coefficient alpha rho grad square of, and it is one dimensional answer. Alpha is any property, phi is any property, alpha is a coefficient. The simple transient distribution happening. So if I say a transient distribution of a temperature of an insulated rod once again is happening, okay, this time a transient, not a steady state distribution. It's a transient. With time, it is changing. So this it is governed by this diffusion equation. So this happens when the rod cools down after an initial uniform source is switched off. There was some, because the rod is insulated. Let me make a rod once again. This is a rod. It is again insulated. But if it is insulated and we want to maintain a temperature in that rod, there should be some source term. Okay? There should be some source term. That is why it was earlier able to maintain the steady state situation in the equilibrium problem. But if there is no source term, that means in the right hand side also I have not written any source term. Okay, that means the source term has been switched off. So after some time, that rod will cool down. Okay, that rod will cool down. So if initially temperature was maintained like T is equal to T naught here and T is equal to T naught again. Okay, after some time, everywhere in the rod, the situation will be the rod has cooled down to T is equal to 0. But it has not exchanged its heat with the outer surrounding. So Q is equal to 0 because of the insulation. So how you will represent this parabolic kind of equation over a plot is like, I'll show. So x is equal to 0 and x is equal to L of the rod. So here T naught, and again here also it will be T naught only. Okay. So but that will happen after infinite amount of time. T is infinite, very small. Okay. So initially it will be like this. The graph will be shown something like this, a parabolic behavior. So this is T equal to 0. And with the time, this graph will, as the time progress, slowly, it will drop down. And after infinite amount of time, both the ends of the rod will come to same situation. Okay. Is it clear what I'm teaching? Or do you have any doubts? You can stop me at any point. Santosh, is it clear?
Yes, sir.
Okay. Geetika, is it clear?
Yes, sir.
Getting. Bhupat?
Yes, sir.
Okay. All right. So steady state situation, I have discussed that it consists of a uniform distribution of a temperature throughout the form. Solution can be done after solving that equations. So it will be a boundary value problem. Another way is a hyperbolic equation I was saying about. This was a parabolic equation. Let me write here, parabolic. This is a parabolic. One way can be a hyperbolic equation. So like, so grad, dou to 5 by dou t square is equal to t square dou square 5 by dou x square. So this is a hyperbolic nature. Okay. And it dominates the analysis of some vibrational problems if you have, or it generally appear in a time dependent processes with negligible amount of dissipations. So it's a wave equation basically, wave equation. Wave equation. So above form of this equation is basically governs the transverse displacement of a, if you have a string under tension, and if you apply some small amplitude, or if there is a guitar string is there, vibrations occurs, acoustic oscillations happens, and this is a constant wave speed. This is a nothing but wave speed. Okay, wave speed. So straightforward to compute with the time, the mode of vibrations, and you don't have to go in all this. Just I'm telling this is a wave equation. Okay, these are the two different kind of the problems. Now how we classify both the kind of either it's a hyperbolic, elliptic, or parabolic, that I will explain for a PD. Okay. So after understanding this tutorial, you have to solve your assignment, whatever assignment has been given to you. That will help you a lot. Okay. Just give me a second. I need. Okay. Yeah. Okay. Yeah. Okay. Classification of method for PD equation or simple PDs. Partial differential equation. If you have a general PDE, suppose this is a general PD, dou phi by dou x square plus b time dou 2 phi by dou x dou y plus c time dou 2 phi by dou y square. I'm just writing a two dimensional, okay, not 3-dimensional, x and y, independent variables. And b dou phi by dou x plus b dou phi by dou y, some f I plus some constant g equal to 0. Okay, this is a first we will assume that the equation is linear, and these are the constants a, b, c, d, e, f, which are there. And the classification of PD is governed by the behavior of its highest order derivative. So we will only consider the highest order derivative. These are the second order, this, and this term, when we are classifying that it's a parabolic, hyperbolic, or elliptic. So class of a second order PD can be identified by searching for problem of simple wave solutions if you have, and if they exist, indicates the hyperbolic equation. We have seen just the wave equation. So what do I want to say that if in this equation b square minus 4ac, I'm just taking this term, or let me write, we'll get the notes. So considering second order derivatives only. Considering second order derivatives. So that means only the few initial terms, that is a of dou 2 phi by 2x square plus b of dou 2 phi dou y dou x plus b of dou 2 phi by dou y square. Only this part if I'm considering. Then if b square minus 4ac, if this is greater than 0, is the square of the 4ac is greater than 0 of this constant, then it is a hyperbolic equation. Hyperbolic in nature. Hyperbolic. If it is equal to 0, then it means it's a parabolic equation. You might have studied in engineering mathematics, these things. But still, I'm giving a brief. Parabolic. And if it is less than 0, then it is a elliptic. Okay. Elliptic equation. So that means if it is greater than 0, when we say that our discriminant is greater than 0, general equation we used to say in our grade 9 or 8 classes, that discriminant b square minus 4 is greater than 0, we say there are two real roots. So similarly here, this is a characteristic. So there are two real characteristics of the equation. If it is a parabolic, then it is a one real characteristic. And if it's elliptic, it has no characteristics at all. So some imaginary terms are there, we used to say. So similarly, I'm taking an analogy to correlate with the things. So yeah. So how you can say the classification? Okay, let me write here itself. So you can write two real characteristics. Someone is trying to join. One real characteristic. No characteristics. Okay, no characteristics. So the classification method by searching for the roots of characteristic equation also applies to the coefficients a, b, c, which are the functions of x and y, or if the equation is non-linear as well. So a, b, c can be functions as well. It is not necessary. You can ask me that why you are taking a as a constant. It can be a variable as well. It can have x, y, anything it can have. It can form a dependent variable or an independent variable. Yeah. But when you are dealing with a non-linear equation, so now what is a non-linear equation? Anyone can tell me? What is a non? Yeah, Geetika, you are trying to say something.
Circle equation.
Yeah, can you repeat?
Circle. It's a curve.
Circle equation. What is the definition of a
Like
non-linear equation?
the coefficients are not a function of 5, like, and order is 1. Sorry, degree is 1. Degree is 1.
So if degree is 1, then how you can say it's non-linear? Just by saying degree is 1.
And like, sir, basic linear equation like ax plus b is equal to 0. Like that, x, the power of x is 1.
In terms of, I'm not saying for a linear algebra part. I'm saying in respect to PDs. You are saying with respect to some linear algebra. Ax is equal to b. That is a differential ODE when you are solving Ax is equal to beta. Or I'm not saying ordinary differential. I'm talking about the partial
Sir,
differential.
in partial also, we have to take the degree of like second order. The degree should be one only, no?
So you can directly say that there is a non-linear term or that is not constant. Basically, the constant is not, it is not a constant term which is multiplied with the first degree or the second order term also. Okay, this is a second order term. Or if you have a first order term, so suppose C, you write C dou phi by dou x. Okay, so this C is not C, it is some variable A, not A, again you will miss it. It's a variable X, a variable Y. Okay, so this is a non-linear. When
Sir,
that is not a constant and it is multiplied with some independent variable. Yeah.
sir, what am I saying is that if this equation has a order of two, a degree of two, then will it be linear?
Degree of 2, yeah, you can say that if a degree 2 is there, you cannot completely specify that it's a linear or non. Linearity and
Okay.
non-linearity depend on that constant is is it a constant or it's a variable which has been multiplied with that term. Okay, anyways, you can think over that. But that's a mathematical portion. So second order PDEs in n dependent variable. So this is an independent variable. This is only like two independent variables are there, x and y in this equation. Okay. But if I say how to write for n dependent variables, so how you will write that equation in general form? Second order PD in n independent variables can be classified, can be written as like this. Okay. Summation of j is equal to 1 to some n, capital N, summation of k equal to 1. I'm writing in an index notation. Ajk. This is a constant A. Capital A is a constant, or it can take any value. It's not necessary that it should be a constant as well. Then it will form a linear or non-linear. You have to think over that. Dou phi by dou xj and dou xk. So when you put j as 1, k as 1, it will be dou xx here, dou x, that is dou x square. Then you write j as 1, k as 2, or j as 2, k as 1. That all depends that it's a dou x, dou y, or for three-dimensional second as well. Plus any h equal to 0, last constant value. Okay. Now how you will get, you cannot directly see b square minus 4ac in this. You won't understand if it's a general equation. So we find how we solve this kind of equation. These can be classified on the basis of eigenvalues of that matrix with the entries ajk. So this is nothing but a matrix which has been formed, okay, for different values of I and j. So for different values of j and k, sorry, we have taken j and k. Okay. So we will calculate the eigenvalues of this matrix, and we need to, if we want to find the eigenvalues, find eigenvalues of a matrix. Just eigenvalues, all right. So how you find the eigenvalues of a matrix? Determinant of that matrix minus lambda I equal to 0. Ajk minus lambda into identity matrix determinant is equal to 0. That is the basic process for finding the eigenvalues, if you all remember. Okay. So if any eigenvalue, now All right. The base that how you will identify it is a parabolic, elliptic, or a hyperbolic. If lambda eigenvalues, eigenvalue is lambda. This is eigenvalue. If lambda is equal to 0, then it is parabolic. If lambda is not 0 and all are of same signs, suppose eigenvalues come as 2, 3, 4, and all are having same size, positive sign. 2, 3, 4 are all positive values, or -1, -2, -3. All are of same sign. Then it is elliptic. And if lambda is again not equal to 0, oh, I should write same sign. And same sign, then it is elliptic. And not equal to 0 and sign is same, one of the sign is different. Any one sign different, you can say this kind of equation is hyperbolic. Okay. We have seen and it is elliptic, non-elliptic, and I'll just give you a hint that viscous flows are generally elliptic in nature. Inviscid flows are generally hyperbolic if it is Mach number is greater than 1, and elliptic when Mach number is less than 1. Or thin shear flows are parabolic in nature. That you don't have to go in that 2D of that part. Is it clear? Any doubts still here to anyone? So how to identify in the PDs what kind of equation it is? Or do you have any doubts? Yeah, I want responses from everyone. Bhupat,
No, sir, no doubts.
Geetika,
No doubt, sir.
Mohanna Priya, are you there? Or you
Sir,
have just joined?
is it audible?
Huh?
Sir.
Yeah, audible.
Say you said same sign. Will it be always negative or sometimes it might be positive?
For which case?
For lambda unequal to 0, you said same sign.
Same
So
sign.
will it be always negative or sometimes positive also?
Either it will be 1, 2, 3, or either it will be -1, -2, -3.
Fine.
Okay. Yeah. But it should have all the values should have same sign. Make sure that.
Right. Okay.
Then Santosh,
Yes, sir.
doubt? Any doubt? All clear?
Clear, sir. Clear, sir.
Yeah. Acha, one question no one asked me, that when we were seeing this, we were applying the Gauss divergent theorem over the general transport equation. Okay. So no one asked me that why only Gauss divergence theorem was applied on this and this term. Why not on this and this term? Why not on the first and last term? Only the middle two terms I'm applying the Gauss divergence theorem. This must be a question you must have. It's a valid question. Anyone can give me the answer, or otherwise I'll leave it up to you if you want to think later.
So I'm not getting the question.
Question is, this is a general transport equation, okay?
Yes.
When we did a control volume analysis, we applied GDT on this term and this term, but we didn't apply Gauss divergence theorem on this term and this term. Why?
This one is a convective term, so there should be a connection between the cells. So we are applying a Gauss diversion theorem on the second term, and that one is a diffusion term. So there should be an interlink between the successive cells. So there is a transport through the surface. Say if
Correct.
it's volume basis, it will be on the it is cell centered actually. There won't be any connection between the cells if it is cell centered.
Correct. Correct. But okay, this I understand. But do you want a connection between these two terms?
Uh, I suppose that is no say at one particular point it keeps on varying regarding the transient term, and that is a generation term on the specific point. It is not going to be transported here and
Correct. Definitely. Right. You're right. Correct. So everyone understood what he tried to explain, or do you have any doubts? Here is the question. Yeah. Yeah, someone was trying to speak. Bhupat, you were trying to say something?
Yes, sir. I was also answering this question like that only.
Yes, yes. The answer is right. This is the only reason. The other two understood or doubt that what has been answered, it has skipped over our mind, head. Actually, this is not just mathematics, the physical. If there is a physics behind this, no? Okay, I'll explain. So basically, suppose you have a box in that fluid is flowing and you have discretized everything. There are multiple cells, small cells. Okay. Suppose I take these two cells, okay, and I'm seeing that how the fluid is flowing from this to this. So there is a common phase when the fluid is flowing. A common phase is there. Okay, from one cell to another cell, the fluid is flowing. The fluid is flowing because of the either because of the convective transport phenomena, or because of the diffusion phenomena between the cells. Definitely, fluid is flowing in a bottle. If you have a bottle with you, water bottle with you, a fluid is flowing from this bottle. You have discretized. I'll tell about the discretization part in small parts, and you want to see from one cell of the bottle to the another cell how it has been transferred. So these two terms are dependent over this phase, and phase is nothing but a and surface. It has a surface, and its surface has a surface area. So you don't want exactly the complete control volume of that to see the transport phenomena from one cell to another. Rather, you want to see that how the interconnection, because of that phase, the fluid is flowing from position. And about why we didn't apply it here, because this is the transient phenomena at that particular cell center, that how the property at this cell center is changing. And similarly, this is a generation source term. You don't want to see that for a phase. You want to see at a particular cell how the source has been generated, or how it is affecting, like a heating or a rod or something like that. I hope it is clear. Anyways, we'll proceed further. Now we'll come to finite difference. So in the lecture that has been dealt with the finite difference part. So anyone has done the assignment that has been shared week 2? Or yet to do? Or both the assignments done week 1, week 0, week 1, week 2, all the assignments have been done? Or none of that has been done? You can raise hand, use the raise hand option. No one has done the assignment? Even week 1 also not done? Okay. Anyways, now we'll come to see the overview of the numerical methods. Now we have seen the conservation equations. We have seen how they have been derived, how a general transport equation comes out of it, how we can say that PD, that is a general transport equation, is a partial differential equation, can be classified as elliptic, hyperbolic, parabolic, and so on. But how you will solve this equation numerically? Now that is a step, and that is nothing but a steps involved in computational field, computation CFD. The first thing is you want to create a geometry. Basically, it's a solution domain. So steps in a CFD solution. First, geometry creation. That is nothing but your solution domain. Second is you want to create a mesh. You will create a mesh in that domain. Next is you will discretize these governing equations. Discretize these PDs which you have formed. Governing equations. What does I mean by discretization is that these PDs are converted into algebraic equations. So that you can solve the algebraic equation, set of algebraic equations. And you will get the solution of these equations after discretizing these algebraic equations. Solution of these equations. Solution of this equation. This is a fourth step. This can involve nonlinearity terms. Source terms can be nonlinear. Coefficient of diffusion. Coupling of the equations can happen. And finally, you will visualize in the fifth process. Post processing or visualization. Or visualize of results. So CFD is nothing but this 5-step process. It's a 5-step process. You create a solution domain, geometry, create a mesh on the domain, discretize, convert the PDs into algebraic equations, solve these equations and visualize them. What has happened? Okay. So how solution can be either analytical. If you know that any equation can be solved analytically. That's good. But every equation cannot be solved analytically. Like Navier-Stokes cannot be directly solved analytically. You have to apply a lot of assumptions, conditions, then you can get some solution. But that is why we do the numerical solutions of those things. So discretization basically involves discretizing the domain into cells, okay, into where we are generating the mesh. And we convert into a set of algebraic equations. There can be different kind of meshes now. Meshes can be of different type. Mesh types. And you are describing. Just give me a second. Yeah. So I was saying about the mesh types. The first one is a Cartesian mesh. Cartesian mesh generally look like this. You have some distribute the domain like this. Small Cartesian cells. That is XYZ. Okay. Then you have a polar mesh. Second is a polar mesh. That is nothing but R theta phi. Mesh will something look like this. Okay, and you have the polar mesh will look something like this. Another one can be a curvilinear mesh. Third is which is dependent on some or different variables you can take. Suppose you have a kind of your domain is not linear in nature. It's curvilinear. Another one can be like a stair step kind of meshes. Okay, stair step. So what is basically a curvilinear mesh? Can anyone tell me? Where it is like something psi zeta z, okay? And all the cells produce a curvilinear depending on the shape of the domain. Okay. Next is like something a stair step mesh. Fourth can be stair step mesh. So suppose this is a kind of mesh. Again, because your geometry is not directly a linear geometry or a uniform geometry, your geometry is like somewhat like this. We cannot frame a structured mesh here. First one, Cartesian mesh, sorry. Cannot form a Cartesian mesh because it will be too difficult to solve this kind of picture geometries like this. Yes. And this can be like immerse boundary methods out there, which it involves. And there is something like a structured mesh or unstructured meshes. So structured meshes are basically that each and every cell are in a uniform pattern. Like first is I, then J, then K. You can say I plus 1, I minus 1, I plus 2, I minus 2. So basically it involves number of neighbors is constant for all the integers. If a particular cell I is there, all the neighbors for that cell will be constant. Whereas in the unstructured mesh, it is not the same case. Unstructured mesh, it is not the same case. So what do I mean? Suppose structured number of neighbors are constant. Like if you see this kind of mesh is a structured mesh. If you see this node, so there are this node, this node, this node, this node is common. Total, this node A has how many nodes? 1, 2, 3, 4, 5, 6, 7, 8. 8 nodes. Similarly, if you see, apart from this A node, if you see some another node, this node A, this is the node A. Again, it will have 8 nodes. So every node has equal number of neighbors. That is why it is a structured mesh. The number of neighbors are constant. Whereas in unstructured mesh, neighbors are not constant. Suppose you have this kind, that here some triangular kind of things is there. Meshing can be anything. Yes. So if you have this node has this, and this. But total how many? Like it is like this. So it has 1, 2, 1, 2, 3, and 4. But if you see for this node, this has this, only 3. Neighbors are not constant. Neighbors are for triangulated meshes or polygonal meshes, it seems like this. So it is unstructured meshes are basically used where the geometries are quite complex or very complex geometry. That is. Okay, and there are some block structured meshes also. Block structured. That for a particular block it is structured, but overall it is unstructured. Suppose that I am having like this, this, this. Overall, if you observe, there is unstructured. But if you see for a particular cell, if you see, it seems like a structured mesh for a particular each block. The number of nodes are same, or number of neighbors are same for a particular block. Then there are other adaptive meshing also, non-conformal mesh, conformal, non-overlapping meshes are there. So yeah, I think this mesh part is clear to you guys. Any doubt? And mesh shapes of the mesh can be in 2D, can be triangular, quadrilateral, polygonal, whereas in 3-dimensional they can be tetrahedral, hexagonal, or prism. Shapes can be there. So what do I mean? The cell. This is a cell. This is a cell. This is a some quadrilateral kind of. This was a triangular kind of for a 2D. There can be for a 3D can be a prism also, or tetrahedron also. The shape of the cell I'm talking about can have different cases. Now we will come to the finite difference method. So suppose if I take, I'm solving my equation, although the interest of the domain is through finite courses of finite volume, I'll just give a brief of finite difference. So if I want to discretize the equation, how I will get the solution and convert that PD into a OD using finite difference method. Suppose if I take a 1D diffusion equation with a source, one-dimensional diffusion equation with source. So again, we will think of the general transport equation. It is said that it's a diffusion and source. So we will take only the right-hand side part of the equation. Left-hand side of the part will be 0. Okay, that means only, and it's a one dimension, so it will, the independent variable is x. Go to 5 by 2x square plus some source term 5 equal to, this was the right hand side of the general transport equation. Okay. All right. Now how you will, first you will create a mesh. Okay. That was the second step. After creation of the geometry, you will create a mesh. How the mesh will look like? So suppose you have left boundary and a right boundary, left boundary and a right boundary, because it's a x only a one dimensional. That is why you have a lot of points. Suppose my point of interest is I. My point of interest is I plus 1. The point of interest is I minus 1. And a lot of other points are also there as well. Okay. A lot of other points are there. Now, what basically I want to do is that I want to solve this equation. This equation should be solved. This PD should be converted to a set of algebraic equation so that you are able to solve it in the computer. How you will do this? That is, so first I want to see by the Taylor series expansion, this property phi for I plus 1 node, for this node, I plus 1. What will be the phi, the property phi at I plus 1 node? It will be phi at I plus dou phi over dou xi into delta x plus dou 2 phi over dou xi square into delta x square by 2 factorial plus so on. Okay. I got value at phi at I plus 1. Similarly, I'll get a value at phi at I minus 1 because I only know phi at I initially. Either through a boundary value you are giving, you are saying that at t is equal to 0. If that I is not here, suppose this I is at here, you know that at the left boundary, if a rod is being heated, temperature is T naught because you are measuring from the thermometer or so whatever instrument you are measuring. You know that on the right hand side you are want to give like this. This is a boundary condition, boundary value problem. So at ith point, I'm taking a general point basically. At ith point, you know, from ith point you are getting the value at I plus 1 and I minus 1. Okay. So phi of I minus 1 will be again from Taylor series expansion, phi at I minus dou phi by dou xi delta x plus dou 2 phi by dou xi square delta x square by 2 factorial and so. Now what you will do, you will subtract both these two equations. Suppose this equation is 1, this equation is 2. You subtract 1 minus 2. So what you will get? Phi of I plus 1 minus phi of I minus 1 is equal to, this term will get cancelled, this term will add, this term will get cancelled. Basically, we are converting this PD into a general algebraic equation to solve. Okay. That was the third step. So that will be 2 dou phi by dou xi into, or I should write like this, 2 delta x into dou phi by dou xi plus other higher order terms as well if you don't want, suppose. Okay. So this gives you the first differential part, the first order of the PD, dou phi by dou x. So what will be dou phi by dou x? Dou phi by dou x, I is nothing but phi of I plus 1 minus phi of I minus 1 over 2 times delta x plus some other higher order term, plus some other higher order terms. Okay. But in the equation, if you see in our 1D diffusion equation, there was no first order term. For solving, we want a second order term. For just giving a hint that how what you are getting how you'll get the first order term. I did like this. Similarly, for getting the other second order term, you will solve again. Let us see plus other higher order terms. What is the order of accuracy for this dou phi by dou x? Can you tell me? Anyone? What actually is order of accuracy? What do you mean by order?
It's 1
Why?
because the order is 1.
Order is one. What is actually a order of accuracy? What do you mean by this?
So if it is a first order, if you stop with the first order, then the order of accuracy is 1. You are not considering the second order.
You are saying the order of this term is one. That
Yes.
is why it is first order.
Yeah.
Okay.
Yes.
No, that's not the order of accuracy. Anyone else? Bhupat?
No, sir, I don't know that.
Don't know. Santosh, what is the order of accuracy?
No, sir, I could not join.
Okay. So order of accuracy is basically what order of the higher order terms you are neglecting. That is because there are some higher order terms here. Okay. So that has been neglected. And what was that first higher order term you have neglected is the order of accuracy of that system. So what we have neglected, I have not written here. Let me write. Basically, when we were solving this equation, there must be another term dou 3 cube by dou x cube del x cube by 3 factorial, right? Del x cube must be here. Similarly here, both must have been added because one was with positive sign, one was with negative sign, and when you are subtracting, both will be get added. So that will give you something. Let me. That will give you some first term as delta x cube by 3 factorial dou cube pi by dou x square, or dou x cube, right? And some other terms as well. So the first higher order term was this. First higher order term was of order 3. Okay. So when you took all the terms on here, you took all this term on the left hand side, basically here, dou cube phi by dou x cube, and here it was dou x cube by 3 factorial. And you divided by this delta x because you divided by 2 delta x here as well as here also, no? You will divide 2 delta. So 1 delta x cancel out. So that is delta x square by 2. This term, which is left, is of second order delta x square. And that is why order of accuracy is second order for this. Okay. Similarly, I'll write for the another term as well. Let me remove this part just for your understanding first. Suppose now in the general diffusion equation, it was the second order equation which you want to convert into algebraic equation, not the first order. So let us convert that, get that value also. Just I got only a first order value. So how I will do that? If instead of subtracting, if I do the operation of addition, instead of subtracting, here I was subtracting 1 minus 2. Now I will do an operation of 1 plus 2. So what will I get? Phi of I plus 1 plus phi of I minus 1 is equal to, you are adding, so 2 times phi of I plus, then this term and this term will cancel out. Then you are adding. The other two terms will add up. So that will be del x square rho 2 pi by dou x I square plus. Now instead of cube, earlier we were getting the higher order term of dou cube phi by dou x cube. But this time they will cancel, and instead of that, the power will be of dou 4 phi over dou x4. That will add up. Okay. So if you are able to understand, so here there will be a term of order of del x to the power of 4. Del x to the power of 4. Okay. Now you are interested in getting this. Let us get this. So what it will be? Phi of I plus 1 rho 2 phi by dou x I square is equal to phi of I plus 1 plus phi of I minus 1 over del x square, this del x square. I'm transposing. Minus, what you will get? 2 times phi of I over del x square. Okay. Then another term will be, or I can write it like this as well. Why I'm writing separately. Phi of I plus 1 minus 2 times phi of I plus phi of I minus 1 over del x square. Right? Next order of del x4, it should be in minus, because when it is transposed here, it will be negative. Minus over del x square. Right? So if you see, we have and some other higher order term as well, but we will neglect this term as well. This is the first higher order term I'm neglecting. Now if you see, numerator is del x power 4, denominator del x square. So that means it is del x square. That means the order of accuracy will be del x, will be second order. So this is why it is second order, not because I'm taking this as second order. Anyways, that will be order of accuracy will be del x square after doing a division process. So finally, you got the equation as this equation. Equation is converted into an algebraic equation. Now this is an algebraic equation. This is an algebraic equation you can solve. Okay, simple algebraic equation. And now you will put these values in here in this equation. You will put this value in this equation. Let us put gamma. Our equation was what? Gamma times rho 2 phi by 2x square plus source term phi equal to 0. This was our equation. Put this value in here. Okay, what you will get? You will get gamma times phi of I plus 1 minus 2 times phi of I plus phi of I minus 1 over del x square. Okay, plus source term phi equal to 0. So source term at I this time, not phi. I am writing phi. So to 0. Anyways, at ith point. You can write it like this. 2 times gamma rho phi, sorry, so gamma by del x square phi of I is equal to gamma over del x square phi of I plus 1. I'm just separating the values. Plus gamma over del x square phi of I minus 1 plus. So this is your algebraic equation, simple algebraic equation. Okay. You have converted your equation to an algebraic equation. Any doubts till here for the lecture? Any doubts?
No, sir.
And you will solve this algebraic equation in your computer, get the result. That is why we use the computational tools, computational codes like OpenFOAM or whatever. But our main focus of the course is on FVM, not FDM. There is nothing like a control volume I have discussed in FDM. There is this set of points. You have created a mesh for over a set of points. There is no control volume and got the values out at all those. I hope it is clear. And there is one method called method of undetermined coefficients of undetermineds. You can find for any order, any value. I think that has not been done in the lecture videos. There is no point to discuss. You can go through it if you want as an extra addition. But our main focus will be on FVM. So what all we discussed in the whole lecture, starting from just giving a brief of what are the governing equations, mass, momentum in XYZ, internal equation and equation of state. Then we wrote a general differential equation. Then we finally came to time dependent, did the integral volume over that. Then we came to a time dependent integral volume integration. We discussed about the classification of problems, equilibrium marching problems. Those are unsteady and steady state problems. Then we discuss about the classifications of PDs, either hyperbolic, parabolic, elliptic. Then we discuss about what are the steps involved in CFD solution, what are different kind of meshes, and finally, how you take out convert the PD into a algebraic equation using finite difference scheme for a 1D diffusion equation with a source system. So this tutorial has been recorded and it will be available on my YouTube channel, and you will get this lecture notes also. A mail definitely comes where you see there is a link of that YouTube channel for all the tutorial weeks as we progress. And the Google Drive link for the lecture notes. So my channel, if even you are not able to find out where is the link, you can mail the NPTEL team, post it in the discussion form, post me in the next tutorial. You can check out my YouTube channel where this tutorial will be posted. There is recording as well as previous recording. The channel name is on YouTube. You can find it like www.youtube.com/@NPTEL. Channel name is this NPTEL with Varnit. All this lecture videos. Any doubts for the session? Bhupat, Mohan, Mohanna
No,
Priya,
sir.
Santosh. Mohanna Priya?
Yes, sir. And I have one question
Yes, please ask.
regarding the grid.
Regarding
Regarding the grid making.
grid making. Okay.
Yes. Say, is there any compatibility kind of index kind of thing for the grid?
Index kind of thing means?
So I come across a word called a grid compatibility index. I don't know what is it really.
Grid convergence.
Grid convergence.
That is something different. That what kind of that means that basically what will be the spacing between each point? Okay. So what kind of spacing, that dx spacing, because everywhere there is dx. Either it's a uniform spacing, non-uniform spacing when you are creating the mesh. What kind of spacing will give you the results every time, the converged results every time? That is a grid convergence test that you have to do when you perform the simulations. Yeah.
Right. Thank you.
Okay. What about Santosh? Any doubts?
Sir, I'll go through it. Then I will ask you.
In the next tutorial. Yeah,
Okay.
you can ask me in the next video, no issues.
Yes.
So every Tuesday we are having from 6 to 8 p.m. So make sure that everyone comes with reading, seeing the lecture videos and doing the assignments and being always on time on this tutorial sessions. Yeah, being consistent is important. The course is not pretty difficult. It's moderate. Anyways, we can end the session then, and we'll see you in the next session.
Thank you, sir.
Okay,
Thank you.
bye.
Good night.
Good night.
Thank you, sir.
Thank you, sir.